Okay. So, welcome back to the session. So, in this session we will discuss about the signal flow graph. In the previous session we discussed about the block diagram reduction rule, and we had taken an example. With the help of that example we apply the reduction rule, and then we calculate the transfer function, right. Then in this session we will discuss about the signal flow graph, right. So, what is here signal flow graph? Signal flow graph, we can say this is the alternate method for reduction of block diagram for calculation of transfer function, right. So, if we are having a complex system and it is having a, you can say, certain gain block, then what we need to do, we have to apply those 8 reduction rule, and then we would able to get the transfer function, right. So, in the previous example we had seen that we were dealing with G1, G2, G3 and G4. Suppose we are having the 100 or 200 blocks. In that case, to apply the 8 rule and to reduce them and to simplify them would be a very complex part, right. So, to simplify the calculation of transfer function, we are going for SFG, that is signal flow graph, right. So, this is a graphical system, right, and we can say it is the alternate way for block diagram reduction for calculation of transfer function, right. So, here this is, you can say, for simplification of complex system, alternative method for block diagram reduction, or you can say it will show the relationship between the system variables. So, what are the system variables? System variables are those which will change or which will affect the response of the system, right. Suppose I am designing electronic system where my current is the input, it will amplified by the BJT or amplifier, right. Suppose gain is beta, so my current would be amplified by beta times, right. So, these are the system variable which will change the response of the system. In terms of block diagram, we can say the summer point where my signal are adding together, or takeoff point where my signal is going into multiple blocks, right. So, these are the system variable which may affect the output response of the system. Okay. And I already told you it is a graphical method, and there is no reduction rule we have to apply in signal flow graph, right. Why? Because this signal flow graph contain the gain formula. So, with the help of this gain formula we will calculate the transfer function, right. So, transfer function will come automatically via this gain formula. It means we do not have to apply any reduction rule in signal flow graph. So, signal flow graph is a very one better step as compared to block diagram reduction to obtain transfer function, right, and it is developed by S.J. Mason. So, that is why this is also known as Mason gain formula, right. So, with the help of Mason gain formula we would able to calculate gain or transfer function of the system, right. Now, we will see the basic properties of the signal flow graph, means how to obtain this signal flow graph from block diagram, right. So, here we can say if I have to draw the signal flow graph, I would require here first a block diagram. If I am having the block diagram, then from block diagram directly I will convert it into the signal flow graph. Second option is if I am having the system equations, then I can obtain the signal flow graph. So, signal flow graph can obtain from the system equations. In that case, this is the condition, equations should be in S domain, right. Suppose I am having the differential equation just like d2 x over dt square. So, I first convert into the S domain via S square, and if we assume initial conditions are 0, then with the help of that we will get a linear equation, and from this linear equation we can draw the signal flow graph, right. It means from these two sources we can draw the signal flow graph, right. And this signal flow graph function, just like follow the property of transfer function, it is valid for linear system, right, or you can say time invariant system. So, whenever we are dealing with the non-linear and time varying system, in that case signal flow graph will not gives us the correct response. Okay. Then we will see some components of the signal flow graph. One is the node. So, node is what? It may be a system variable which is equal to the sum of all incoming signal at the node, right. For example, if we see in the block diagram, summer point is here. So, I can replace this summer point via a node. Okay. So, you can say it is receiving u 1 and it is receiving u 2 here, and output is you can say minus of u 1 plus minus u 2. So, here in the node representation what I can represent, it is having the 3 signal, one is minus of u 1. So, this minus sign I have to add here, plus minus u 2, it means plus minus sign I have to add in front of u 2, and then I will get here minus of u 1 plus minus u 2. So, I am representing or replacing this summer point via a node. So, where summer point will act as a system variable. In the same way, if I am having here a takeoff point, so this takeoff point can be represented in terms of node, right. Suppose u is the input passing through it, same input is passing through it. So, I can draw here a node receiving input u, same input u is passing through it, right. So, takeoff point and summer point can be replaced by a node, right. Then second component is here a branch. What is branch here? So, branch you can say whenever signal travels along a branch from one node to another in the direction of arrow, we can say that would be a branch. For example, I am using this node, this is second node, signal is passing through it, right, and this is the direction of signal. So, in between two node I can say this is the branch which may have gain g, which may have gain of unity, right, whatever. So, we can say this is the branch which is connecting the two node, and direction over the branch will tell you direction of flow of signal through it. Okay. And each branch has a finite gain. Whatever branch we are designing with the help of signal flow graph, it will have a finite gain. So, here if I am writing g, it means g is the gain. If I leave this blank and does not write anything, it means 1 is the gain of branch, right. So, this consideration we have to keep in mind, and whatever signal passing through branch, it will multiply by its gain. Suppose the gain of the branch is g, my input is u. Whenever I am moving from u to the right direction, so at this node I will say the value of signal would be u times of g. It means u signal passing through this branch is having gain g. After passing this or covering this node, my output would be u times of g, right. So, these are the rule that we have to keep in mind in signal flow graph, right. Now, we will see the basic terminology we have to use in signal flow graph. One is the input node or source node. So, here if I am having a certain node, that may be a summer or takeoff point, right, and from this node what is happening, all the signal are going into the system, right. It means it is having all the outgoing branch. So, we can say this is acting as input node or it is acting as source node. Okay. And second is output node, or you can say sink node. Whenever we are having a node which is receiving all the incoming branch, that may be a summer point or takeoff point. So, we can say this is the output node or sink node, because all the signal terminating at this node. So, this will be known as output node. Okay. Then next is here path. What is path? Whenever we have to connect certain nodes to reach a certain point, then we have to travel in certain direction, and that direction will contain certain gains, and we can say that would be a path. For example, this is my source, you can say input node, intermediate node, and this is my output node, right. And suppose they are having a certain gain, suppose it is gain g 1, direction is this, gain g 2, direction is this, and I want to know what is the value of path. So, what I will do? I will travel from input to output. First I will encounter g 1, my suppose input is u here, then g 1 will be gain, here signal would be u times g 1, okay. And again after traversing here, gain is g 2, my value would be g 1 u g 1 g 2, right. So, what would be my path gain? If you see here, my path gain is or path is g 1 dot g 2, Okay. So, this is the path present in signal flow graph, and whatever gain coming in the path we have to multiply it, and we have to keep one more point in our mind that during traversal of the node our node should not repeat, right. For example, if I add a feedback path in between the nodes, suppose a feedback path is present here, right. So, when I follow this path, suppose it is having gain G 1, having gain G 2, and it is having gain of H. My input is passing through this U times of G, and again it is what doing? It is keep repeating on the same node and then going to the output. So, whenever I am traversing this gain, so H will come in the picture and I am repeating this node 2 times. Okay. So, this repetition is not allowed in calculation of path, right. So, here we have to keep in mind whenever we are defining the path, it should cover node only one time. Whenever this repetition is happening, that would be invalid path, right. Then forward path. So, whenever we are moving from input node to output node, then this would be known as forward path, right. And what is feedback path? Whenever we are keeping any signal from output going back to certain input, so we can say this would be a feedback path, right. You can say reverse direction, you can say from output towards the input, that would be feedback. Then self loop, if we are having a certain node which is having the single loop, right. It means signal originate at the you can say same point, or you can say signal originate at this node and terminate at this node, right. So, we can say this is a self loop. Basically, what is a loop? We can say a loop is a you can say graph which will have signal a single originate point and single terminate point, right. So, for example, this is my intermediate node, I am starting from here. Okay. Suppose it is G 1, I am going to this node, coming back to this node, right. It means I am starting my journey from same node, going back and coming back to same node. So, this thing is known as loop, right. And what is self loop? If loop contains single node, if this loop contains the single node, we can say this is self loop. So, we can say this is self loop and this is simply a loop, or you can say a feedback loop, because it contains two nodes. So, we can't say it is a self loop, right. So, I hope the definition of loop is clear to you, right. Then path gain, you can see the product of branch gain encountered in traversing a path is called path gain. So, I already discussed in definition of path. If I am going from input to output, it is having certain path, you can say this branch is having gain G. What would be path gain? Whatever gain encountered from input to output, their product would be the path gain. When we solve the numerical over it, with the help of that we would be able to say what would be the path gain. For example, if it is having multiple nodes, path gain you can say it is having G 1, G 2. So, whenever I am going from input to output, I have to encounter two branch having gain G 1 and G 2. So, what would be path gain? We can say it is G 1 dot G 2. So, this would be path gain for this example. Now, we will see the Masson gain formula. This gain will calculate the overall transfer function. So, this formula is given by this function, transfer function equal to this term summation from k equal to 1 to n p subscript k delta subscript k over delta. So, one by one we will see what are this parameter, right. So, here you can see there is no requirement of any reduction rule. Via this formula, gain formula, directly we will get the transfer function. Okay. So, p subscript k is the path gain of kth forward path. It means to reach from input to output, I may have path P 1, I may have path P 2, I may have path P 3, and whatever possible paths are available, I have to sum it using this formula, because the summation is you can say all the possible value of p subscript k. Okay. And what is n? N will tells you number of forward path right. So that number times you have to add P1, P2, P3. Suppose n value is 4, so I have to add 4 value of forward path, that is P1, P2, P3, P4. This would be more clear when we do the numericals. Okay. Then delta, this will tell us the determinant of the graph, okay, and its value would be 1 minus sum of individual loop gains. So, whatever loops present in the signal flow graph, we need to calculate their gain and do the sum operation, then we will get value of sum of individual gains. Then we have to select sum of gain product of all combination of two non touching loops, right. For example, this is one loop, self loop, and this is second loop. Suppose its gain is H1 and its gain you can say is H2 and G1 is the forward gain, right. So, these two loop we can say they are non touching loop because their nodes are separate. If this self loop is starting here, so we can say there is no non touching loop because all the loops are having common node. Whenever two loops are having different nodes, so we can say they are under category of non touching loop. Then here in this case we have to calculate product of their gain. Here my gain is H1, here product of gain is G1 H2, and I have to calculate their product, that is H1 dot G1 H2, right. So, when we do the numerical, then this concept would be clear. After that, minus sign sum of loop gain which is having the 3 non touching loop. Suppose I am having a one more loop here, right. So, we can say this is the loop 1, this is the loop 2, this is the loop 3, right. So, we can say this one and this, they are 3 non touching loop because their nodes are different. And how to calculate? We have to calculate their product, right, and then we have to take their other combination, sum them, then we will get this term sum of gain product of all combination of 3 non touching loop, right. Then we will see last term del subscript k. So, this will tells the value of delta part which is not touching the kth forward path. Suppose I am having forward path P1, P2, P3, right. So, what would be delta 1? Delta 1 means all the loops which is not touching the forward path, okay. That I have to apply here in calculation of delta 1. For delta k, the formula would be same, that is 1 minus sum of individual loop gain. Suppose this is my input to output path, right. Suppose it is feedback, it is having certain loop having gain h and feed forward path you can assume, right. So, here my forward path would be what? One is this one, you can say suppose its gain is G1, here its gain is G2, G3. So, here my two forward paths are present, one is P1 equal to G2 G3 and P2 equal to we can say G1, right. So, with the help of these two paths I can reach to the output node. In between I want to calculate delta k, right. So, whenever I am considering this forward path P1, so what would be delta k? It is the loop which is not touching the forward path. So, here one loop is this h which is not touching my forward path. So, I can say for path P1, the delta 1 would be this formula 1 minus sum of all the loop gain which is not touching the common point or common forward path, okay, it is h. So, this loop is not touching the path P1, right. Whenever we follow this path P2, so here we will see there is no loop which is not touching the forward path P1 because at this position h loop is touching this forward path P2. So, we can say here delta 2 is equal to 1 and remaining terms are 0. It means there is no individual loop, it is 0, it is 0. So, we can say del of 2 is equal to 1, right. Again this thing would be more clear when we solve the numerical. Now, we will see a basic rule for construction of signal flow graph. Right here we can say this equation is right y2 equal to this much. How we can obtain from signal flow graph? Suppose we are having node y1, y2, y3, y4 and this signal partial SFG is present here or signal flow graph is present here. So, we can see this signal is coming from y4 terminating at y2 and signal is coming from y1 terminating at y2. So, y2 is acting as output node because it is receiving or it is having all the incoming branches. So, here I can write y2 would be equal to y1 times of a12 because y1 signal is passing through it, it will amplified by a12. So, I can say a12 is the gain, y1 is the signal passing through it plus second signal coming from y4 with gain of this much, right. In the same way we can write the second equation. So, here again I can see my y3 is the node which is receiving all the branch. So, y3 can be equal to a23 times of y2 and a53 times of y5, right, because whenever signal passing through branch it will multiplied by its gain. Similarly, this one, right. So, here y4 can be written as a34 times of y3. So, this is the way of writing or designing the signal flow graph. Now, this is the example that we can take. So, here x1, x2, x3, x4, x5, x6, x7, x8 they are the nodes. Okay. So, here I am assuming value of signal is unity and in between x1 and x2 gain is A, between x2 x3 gain is B, x3 and x4 gain is C, then x4 to x3 feedback gain is D, then x4 to x5 gain is E, then self loop gain is F, then gain is G, gain is I and J, right, and again our feedback would be H. Now, what would be here forward path? So, this would be my input, this would be my output and I have to seek number of forward path and I have to keep in mind no node should repeat in calculation of forward path, right. So, here I will say forward path P1, I will traverse from x1 to x2 gain is A, then x2 to x3 gain is B, then gain is C till x4, then x4 to x5 gain is E, then x5 to x6 gain is G, then x6 to x7 gain is I, then x7 to x8 gain is J, right. So, this is my one forward path which will help us to reach from input to output. Okay. And second forward path, if we see, we can follow this path till here, then we can follow this path, but what is happening? Repetition of node. So, we can't consider this thing as a forward path, right. So, here we are having only single valid forward path, right. Now, we have to calculate number of loop gains. So, you can see one loop is here, this one with gain C and D. So, I can say this is the loop 1 L1 which is having gain of C dot D. Then I will see second self loop is here, this is L2. So, L2 having gain of F. Third is the loop, you can say I will start from node x2, go x3, x4, 5, 6 and return back to x2. So, what is the total gain? You can say B dot C dot E dot G dot H. So, this would be my third loop, that is B dot C dot E dot G dot E dot H, right. So, three loops are present here. Now, I have to notice the two non touching loop. So, you can say this loop L2 and L1 they are having separate nodes. So, we can say the non touching loop NTL is equal to L1 dot L2. So, you can say L1 is C dot D, L2 is dot F. So, this is the gain of two non touching loop, right. So, I hope this would be clear to you. In the same way, this signal flow graph is given to us. Now, we have to calculate the transfer function, right. So, I will use here the Masson gain formula that would be given as transfer function equal to summation of k equal to 1 to n p subscript k del subscript k over del. So, first we need to determine p subscript k. So, here you can see only single path is available because other paths are looped. So, I can say number of forward path is 1, right. So, here n is equal to 1, it means this whole thing would be what, p 1 del 1 over delta, right, because if n is equal to 2, then here we can write p 1 del 1 plus p 2 del 2 over delta. Now, determine p 1, p 1 is what, here gain is 1, g 1, g 2, g 3, g 4, g 5 1. If you do their product, you will get the first forward path p 1, only one forward path is present. So, we have to switch to next step, we need to calculate here value of delta or delta 1. So, for calculation of delta you need the loop gain. So, individually we will calculate the loop gain. So, here L 1 is equal to minus G 1 H 1, L 2 is equal to minus G 2 H 2. How? You can say, suppose this is the loop 1, I am going from this node to this node with gain G, returning back gain of minus H 1. So, I can write here gain is minus G 1 of H 1, right. In the same way, when we go for loop 2, again I can see G 2 is here, minus H 2 is here. Okay. So, here we can say this is the loop 2. In the same way, we can see loop 3, that is G 4 and H 3 minus G 4 dot H 3, their product. Then loop 4, you can say you will start from this node, go here, return back, we can say gain is G 4 G 5 multiplied by minus H 4. So, this is the loop 4. So, these 4 loops are present here. Now, we have to remember the formula. Okay. Right. It means sum of all individual loop gains, it means we will write here L 1 plus L 2 plus L 3 plus L 4. Then we have to determine is there any non touching loop pair, then we have to multiply their loop gain, then we may write L 1 dot L 2 plus L 3 dot L 4 if they exist. We will see in the example whether they are existing or not. In the same way, when we go for the third part, sum of all combination of 3 non touching loop, we can say L 1 dot L 2 dot L 3 plus L 2 dot L 3. If non touching loop are existing in the system, then this may be the value. Okay. So, I hope this formula would be clear to you. Now, see in the example, in the current example, the 2 non touching loop we can say one is L 1 and this L 3, right, and we can say this one is L 4. Second would be L 1 L 4, then L 2 L 3 and L 2 L 4. So, L 2 and L 3 is here, these are 2 non touching loop, then L 2 and L 4 you can say L 2 and this loop 4, right, and then you can say L 1 this loop and loop 4. So, this would be the pair of non touching loop. If you see, is there any 3 non touching loop? No, there is no 3 non touching loop, right. So, we have to calculate this thing L 1 L 2 L 3, sorry, their product gain L 1 L 3 L 1 L 4 L 2 L 3 L 2 L 4, and then we have to put in Masson gain formula and we will get the transfer function, right. So, in this SFG we can see there is no 3 non touching loop. So, delta would be given by 1 minus sum of all individual loop gain, okay, plus sum of all product of 2 non touching loop gain, right. So, this would be the term and there is no 3 non touching loop. So, after that minus sign you can put 0. So, this would be the value of delta, that is determinant. So, what would be value of delta 1 if you see? So, for delta 1 you have to see, is there any loop which is not touching the forward path P 1? No, here every loop is touching the forward path P 1, right. So, we can say the value of delta 1 is equal to 1, right. So, from here we know value of P 1, we know value of delta 1, we know value of delta. So, put in this formula to calculate the transfer function, right. So, here we can say delta 1 is 1, remaining term would be 0, because there is no loop present in the signal flow graph which is not touching the forward path, right. So, hence transfer function would be given by this formula. If you put all the term together, this would be overall transfer function, right. So, this is the one example. Second, using a block diagram, how we can reduce it, right. So, you can see this is a feedback path, a feedback loop. So, here I can replace this summer via a single node, okay, and this takeoff point via single node. Here gain block is G, right, feedback gain is H. So, in this way I can convert a block diagram into a signal flow graph, right. So, here this is the example that we will see in the next lecture. We will solve this example using signal flow graph to calculate its transfer function, right. I hope these things would be clear to you. So, in the next lecture we will see reduction of this block diagram using signal flow graph. Thank you for today.